Speaker come up. Andras, Pataki.
Oh, sorry. No worries.
Am I in? Okay. Okay, so I'm Andras Pataki from the Simons Foundation Flatiron Institute. So first I want to briefly describe who we are. The Flatiron Institute is a research arm of the Simons Foundation, which is a philanthropic organization of the Simons family who had a very successful career in the hedge fund industry. And it's on? Maybe a little higher. Is it better? Okay. Oh, very good. Okay. And the Flatiron Institute's mission is to advance scientific research through computational means. And we are called the Flatiron Institute because we're in Midtown Manhattan, one block from the Flatiron building in New York City. We're organized into centers, computational centers for astrophysics, biology, quantum chemistry, and mathematics. And I'm actually from the scientific computing core, the group that kind of builds the infrastructure and makes all the computational facilities available. We're a relatively young institution. While the foundation existed for a few decades, this in-house research group is about 4 or 5 years old, started as a small group of about 20 scientists. Right now we have about 150 across the various disciplines in our brand new building in Midtown. And we deal with a variety of disciplines from biology to astrophysics, so genomics data sets. We pay for a lot of genomic sequencing for a large autism initiative that the foundation has, Autism Research Initiative. We have astrophysicists who do coupled MPI simulations of the early universe, cosmology, etc. So our cluster handles a variety of computational styles from embarrassingly parallel, more high throughput computing type things like genomics pipelines where you have to process lots of genomes in parallel on the same pipeline. Loosely coupled MPI like protein folding and some of the quantum chemistry codes, and traditional HPC type compute loads, which are astrophysics simulations that are tightly coupled MPI. And in Midtown, we have about 20,000 cores. In San Diego Supercomputing Center, we also have about another 20,000 cores. So about 40,000 cores of computing, a couple of hundred GPUs, and we have a fairly large Ceph setup to support the storage, about 30 petabytes raw space. We also have other file systems like GPFS and Lustre at other locations as well. So this is kind of the generic Ceph picture. On this picture, our usage is kind of heavily on the CephFS side, since most of the traditional codes don't really deal with object stores and want to run in parallel on multiple nodes. CephFS was kind of the attractive choice. We do use block devices for some special cases as well, and we don't really use Rados Gateway ourselves. So on the Ceph technical side, I wanted to talk about one thing that is kind of not emphasized all that much, which is how good the recovery of Ceph is from failures. And not in the sense that just Ceph is very resilient, but also what the costs of this recovery is and how well how the situation is when there are multiple failures. So in the traditional RAID-based approach, you have a bunch of drives, and when a drive fails, you have to kind of read all the other drives or most of the other drives from the RAID group to recover to a new drive. On today's 8 to 12, even 14 terabyte drives, that might be close to a day of processing. And if during that time, you're heavily reading the drive, so you're exercising the other disks, if there's another failure, you have to start again and spend a whole other day or so to try to recover from a double failure, and kind of at that time you're biting your fingers to make sure that there's no third failure and lose all your data. So the Ceph situation is a lot better than this because of the way the declustered placement is of the data. This is a triple replication slide because otherwise it would be too busy. Various parts of the file are broken up into, by default, 4 megabyte pieces and written across different disks. So if there's a failure of a single drive, you still have to re-replicate the same data that's missing, but you can do that in parallel. So by the crush algorithm changing the cluster map, in parallel various OSDs will re-replicate the data. So you're replicating the same 8 terabytes, but in parallel, so it might take something like an hour instead of something like a day. Now, that in itself is nice, but what's nicer is the situation when you have a double failure. So if you have a double failure so 2 drives fail about the same time, then you're really one failure away in a triple replicated case from losing data. So in the RAID case, you have to still wait your 24 hours to re-replicate. In the Ceph case, in the triple replicate case, you only have relatively few placement groups where 2 copies happen to be on those 2 drives. And those are the ones you absolutely have to recover to ensure that you're not losing data. So the amount of data that you really have to recover actually reduces as the cluster grows. So if you have a larger cluster, the chances of 2 copies of the placement group ending up on drives that happen to fail actually decreases. So the recovery to kind of a safe state is faster and less likely that you have a third failure at the same time. That's kind of an important point. So anyway, returning to the story of Flatiron, after this brief detour into Ceph recovery. When we started, in the early days, we had some ad hoc computing. We had an HDFS installation, which was not a POSIX-compliant file system. This was in 2014, 2015. We evaluated various alternatives and picked Ceph in April of 2015, which is the birthday of our Ceph installation, CephFS, which was Hammer, and that time CephFS was still experimental, but it kind of worked well for us. We were a very small scale at that point, in the hundreds of terabytes instead of petabytes, on some essentially small rack mount servers and towers. Actually, they were not even rack mount. And we had about 18 drives in each and co-located mons, and so a fairly small scale installation. And as we grew, the research group grew from 20 to nowadays 150, so did our compute and storage needs. And we went from the original small design to a much larger setup, which is still a very space-oriented design, disk space-oriented. So all our disks are spinning disks. We don't have a lot of flash. We do use flash for journaling type things like WALs and DBs for OSDs, but not for data storage. And even for metadata for CephFS, we use flash. We're using fairly large building blocks. These are these Dell nodes that have essentially 45 drives per node, spinning drives. And we have separate metadata and mon storage. So our current setup is about 30 petabytes of raw space in 42 of these very large, deep nodes, monitor nodes, and separate metadata storage on NVMEs. So this is a picture of what one of these storage nodes looks like. It's actually not very different from what's outside, except that besides the 90 drives that are in one of these chassis, there are 2 nodes that 45 and 45 drives are connected to that are full, actually it should say 2 times 14 cores, so 28 core Broadwell servers. that are connected with dual 40 gigabit Ethernet. And all this setup is connected to a fairly large core switch that we have. Here's what one looks like with all the drives populated, and before when it arrives on a big pallet, you have to lift it like a forklift and stuff. Here's some wired up. Lots and lots of fiber. They're very, very deep. They have to take off the back of the racks, essentially, the back doors of the racks so that they fit inside. So now I want to talk a little bit about performance. So these are synthetic benchmarks of sequential read and write performance of this Ceph setup. And they kind of illustrate somewhat how Ceph works and what the good and bad things are. This is a triple replicated read and write performance test from 64 client nodes, so 64 compute nodes at 10 gigabits. So they can each write something like a gigabyte a second in maximum. And it turns out for this setup, they actually do. They do successfully write about a gigabyte, even more than a gigabyte a second per node, so about 70 gigabytes, 80 gigabytes per second, and read about 60 to 70. You can see that on the right side, the Ceph cluster network, you can see that the write is essentially amplified by a factor of 3 since it's a triple replicated pool. These are network plots, so you see that there's 3 times as much network input and twice as much network output, since the primary OSD then sends all the data to the 2 secondary OSDs. And the read is read from the primary always, so the Ceph network throughput always just shows a single read. And the CPU utilization is pretty heavy on the writes, not almost insignificant on the reads. The same story for an erasure-coded pool, which is a 6+3 erasure code. Same client nodes. They still saturate pretty much the client network, reading and writing at about something like a gigabyte a second per node, so 60, 70 gigabytes a second. On the Ceph network, you can see that the erasure coding is handled very differently. The writes are kind of, the network throughput requires about twice, since the primary OSD will kind of break up the pieces into chunks and write each of the chunks out. One goes locally, and most of the others will go to other nodes. So more or less double the network bandwidth. And the reading is also heavier because now the primary has to ask for all the chunks, reconstruct the erasure code, and send back the result. And the CPU utilization writes is heavier, but now reads are also require some CPU for the erasure code calculations. The red line is kind of at the load when the cluster will be fully busy on the Ceph cluster. So they're still pretty far. Now, since it worked well on 64, let's try a bit higher. At 96 nodes, this is where the cluster kind of starts breaking on writes a little bit. The load kind of goes over what the machines can even handle. It still gets through more or less 100 gigabytes a second, but at this point, the OSDs start complaining about slow writes, etc. The reading still goes pretty well at this point. And the same story for erasure code. The CPUs are even busier for the EC calculations. The writes are not too smooth at this point. Reads are still okay. Some close to 100 gigabytes a second, or over 100 gigabytes a second, in fact. So we have some unique challenges at the Flatiron Institute, that we are in Manhattan, which is just a few feet above sea level. Space is precious in New York City. You don't want to put the computers in the prime office spaces where people want to sit, so most of our computing is in the basement. So you want to worry, you obviously don't want your data to be flooded and permanently lost. So we kind of distribute all our storage across the buildings in various places, and we use Ceph's crush configuration to make sure that there's enough redundancy that we can recover in case the basement floods, for example. If the basement were to flood, you would lose all our computing, but we would not lose the data because our building is kind of divided into 3 kind of regions, and And the failure domain is these regions of the building. So one of those regions happens to be a basement, which could potentially flood. And with triple replication, each of these three regions gets one replica. For erasure coding, each of these regions gets 3 of the 9 chunks for the 6+3 erasure code. And the actual overhead is about 50% for 6+3 erasure coding, obviously much more for triple replication, but we end up close to the 50% overhead because most of the data is in large files, which we store in erasure code format, and I'll talk about that more in a second. Lessons learned. So we had CephFS for more than 4 years now. We learned lots of things from kind of building hardware and running different releases. One was that you really have to test all the hardware out. That lots of hardware is fairly buggy. And for example, the very first drives that we bought were NAS-grade drives from one of the major manufacturers, in fact. And they silently corrupted data. So you wrote some data and you read them back, and sometimes every so often, in a terabyte or so, some bits got flipped and in fact, some bits got removed and data got moved. And this was in a Hammer. Ceph detected this. And of course, the very first reaction, CephFS is not stable, Ceph is wrong, Ceph is screwing up the data. And it turned out that actually Ceph was right, and the drives were screwing up the data, which we confirmed via independent benchmarking afterwards. So it's very important to test hardware. Drives have firmware, controllers have firmware, and many of them can be buggy. Networking, we also had some things like the early 40 gigabit interfaces were dropping packets. Obviously, Ceph has lots and lots of TCP connections between the OSDs. If you run 45 OSDs on a node, there are thousands and thousands of TCP connections per node. So all the TCP retransmissions end up causing difficulties. NVMEs, obviously, this shows up on the mailings very often that people try to use consumer-grade NVMEs or SSDs, and consumer-grade SSDs probably write slower than even a spinning disk does. We benchmarked some of them at like 10 megabytes a second or something. On the software side, we ran a lot of Ceph versions, starting from Hammer, to upgrade to Jewel and Luminous. We recently upgraded to Mimic, and we are going to Nautilus by the end of this year. We kind of are a little bit always behind the kind of bleeding edge releases because there have been some problematic releases, so we usually test them on our test cluster and kind of try to apply some of our production loads to them before upgrading our main cluster. Kernel versions, we had difficulties with some of the CentOS kernels, so we're building our own kernels that the Ceph nodes are running and tuning them also. Various networking, firmware, and software stack we had issues with, so we also had to test all of those and kind of keep track of which versions work well and which ones don't. Typical failures we see are single drive, and those Ceph handles very nicely. Usually the OSD crashes or reports some error, and the Ceph rebalances automatically, and you just notice, oh, one fewer OSD is running, and replace the drive, start it back up again. Everything backfills in a day, and everything is back again. Sometimes we have node crashes, and those more often than not are not actually a full failure of a node, so we don't rebalance Ceph on a node failure automatically. So that requires manual intervention, because more often than not, there's something a little wrong, and the node can be revived, and moving half a petabyte of data around is usually not the best idea. Usual DIMM replacements, we had a couple of NVMe failures. With the 45 drive setup, we are journaling 22, 23 drives to one high-performance NVMe, so the Intel Optanes. So if one of those fails, that's pretty costly. That happened once. With one exception, we actually, ever since we moved onto this largish Ceph setup, we haven't had an outage on Ceph, a full outage. Every so often we had things like certain files got locked up and the metadata server has to be restarted and things like that we had, but not like a full outage when nothing worked, with one exception which I'll talk about. We've done upgrades of Ceph without shutting the whole system down, so the rolling upgrades have worked really well for us. We had one, so disaster recovery always have these, theoretical kind of stories that what happens if this fails or that fails. We actually had an actual story, which was that we moved to a new building as we grew, and the new building we got floor by floor. So there were tenants on some of the other floors. And unbeknownst to us, there was a bathroom right above one of the data closets. And the way New York City works is there's no drainage to the building, so you have to have pumps and however it works. Somebody left some water on for the weekend, and water and electricity, well, didn't mix very well. So we ended up flooding one of these 90 drive Ceph nodes on one of the floors. And thanks to Ceph and the whole redundancy model, we didn't lose any data. Here's what one of the drives looked like afterwards. It was like, this would be kind of well done, It's this black water standing in the chassis. And that time we got close to losing data, and then we rethought our redundancy model and the crush rules and the failure domains, and we went to this new thing of trying to kind of separate things as far as possible within the building after this incident. So I'm going to go from bottom up here. So Ceph is an open source project which really worked well for us because we sometimes run modified versions of things that help us with our circumstances. One is the whole erasure coding conversion, for example. We try so erasure coding in CephFS doesn't really work very well for small files, and the majority of files by number are small in a typical case. Maybe 95% or 99% are a megabyte or under. But most of the space is taken up by large files. In our case, probably 95% of the space is taken up by maybe a few percent of the files. So it would make sense to erasure code the large files and keep the small files triple replicated. So what we do currently is we have all the writes go as triple replicated, and we do erasure coding of the large files in a week or two after they got written. So we crawl the file system in parallel on a cluster, and actually as a regular cluster job, and move them to a replicated pool, copy them to a replicated pool, and do an atomic move back to the right places when the conversion is done. And I've actually been talking to some developers to do this in the MDS to support the feature of actually moving a file to a different pool without the user actually ever seeing any impact of that. Very often, especially in the early days when we found issues, we got really super good support from the developers of Ceph in forms of early patches. So sometimes we run various bug fixed versions that we build even before they're released. So this has been a very different experience than, let's say, on some of the commercial products that we run, where it takes months, if ever, to get anything fixed. One of the big challenges of file systems, distributed file systems, is monitoring what's happening. So let's say something is slow. How do I decide who's doing it? We have a cluster of hundreds of nodes. Somebody's running some job that does something evil in parallel, like accessing files in all kinds of ways that they shouldn't. They should think about how they're using the file system. It's difficult to find these. So we actually run a modified Ceph client that collects statistics on how people use the file system in real time and sends them to central place, and we aggregate that together. So when there are some issues with the file system performance, we can immediately see who's doing what at that time on the file system. And makes it possible to find problematic jobs and kind of see how we could talk to their users to optimize their I/O patterns. Because obviously, if we have something like 400 or so compute nodes, so if you do nasty stuff on 400 compute nodes, it doesn't matter what parallel file system you put behind it. It's going to be very unhappy. So an example is like this. We get data like this out of it, like by user, the last 10 second in a snapshot of how many files they're opening, how much reading and writing they're doing. We get more than this. We even get kind of more granular data, either by node or even by file we can receive. So an example by this is in the middle there. There's a user who's opening 920 files a second. So perhaps that's a problematic case, and we should talk to them what they're doing, and reading 200 kilobytes per second total out of 900 files. That's clearly not a super good I/O pattern. And then there are some other ones that are writing massive, much more data into largish files that work much better on in the file system. This, something like this, making it into in a more structured way into Ceph release would be nice. Like this RBD top has this. We did this on the client. We are doing this on the client side because we want per user information, not just per node or per OSD information out of this. This is currently we have these patches for a Fuse client that does this. So I want to finish up by talking about our current challenges. What are the pain points of Ceph in our setup? Probably number one is small file performance. We are mostly using the Fuse client with a few exceptions for stability reasons. That Fuse has been very stable. It's very easy to install the latest version of Fuse as it's packaged together with the rest of the Ceph daemons. But it's because of the extra user space, kernel space transitions, it's particularly bad with small files. We've been testing the kernel client. It has been certainly much, much more stable lately than it was a couple of years ago. I'm working on some of this instrumentation also for the kernel to try to monitor users' usage. And we're kind of excited about the small file improvements for Octopus that is essentially a testament of Ceph's flexible design, that you can acquire enough locks that you can do asynchronous file creation and file removal to make tar, untar, RM-rf and things like this really, really fast in a single client. Obviously, with Flash kind of coming to a better price point, we're looking at Flash storage as well somewhat. It's not a huge priority for us, but the Ceph Crimson project is very exciting. And we're always looking at what potential upgrades to these 7,500 building blocks that would be more architecturally up-to-date, probably less disk heavy to have a little better performance out of them. And what would be interesting also for us for CephFS is some support for multiple sites, or in some ways having a unified file system be visible across multiple sites that are too many milliseconds away, so you can't just distribute the OSDs geographically easily, so you need some kind of either replication or something similar. And we also have a tape system that we purchased recently that we want to move some of the data off of, and some functionality to help with that. And Ceph would also be very, very interesting. So we're looking at some of these ideas in the future. So that's about what I have to say. In this case, we're probably short on time, so if you have any questions, we can talk afterwards.
Okay.